Hello. So in this video, we're going to be looking at section 3.2 on finding zeros of polynomials. So I'd like to start by reviewing something we actually did in class on Friday, which is using synthetic division. So what we have on the screen right now is this problem here. We have 9x to the third power minus 16x plus 5. And we want to divide that by x minus 1/3. And so we can do this using synthetic division, which is a shortcut for dividing polynomials. The contraption in which we do synthetic division is this half a rectangle right here. On the outside of the box at the top here, we're going to put the value for c, which remember we have a formula for identifying. We're dividing by x minus c. C is what comes after the minus sign. And so in this case, c is going to be equal to 1/3, positive 1/3. So the trick there, a lot of students remember, is take the opposite sign of that number. Across the top inside the box, we write the coefficients only of the thing we're dividing by, starting with the highest power. So x to the third power goes first. The next one needs to be x to the second power, and since we don't have that in our dividend, we put a 0 there. And then the next term, x to the first power, the coefficient's negative 16, and then positive 5. So don't be too alarmed about the fraction there. Hopefully everything works out nicely. Usually it does. We get the process started by dropping the first number below the box. So we'll put a 9 here. 9 times 1/3 is no different than 9 divided by 3. So 9 divided by 3 is going to be 3. We write that result underneath the next number inside the box. We add this column together. 0 plus 3 is 3. And hopefully these will just keep being divisible by 3. 3 divided by 3 is going to be 1. We add these together, we get negative 15. Negative 15 divided by 3 is going to be negative 5. We add these together, we get 0. So this is interesting. The remainder works out to be 0. So the last number you get here is the remainder. All right, oops, sorry about the extra stray marks there. The numbers in front of the remainder constitute your quotient, but they're just the coefficients. So we have to get the variables back into the answer. And so it goes from highest to lowest power as well. It'll start with 1 power less than what you began with in the original problem. And so we'll start with, this starts with x to the third power up here. So this will start with x squared. So our quotient is 9x squared plus 3x minus 15. All right. And every division problem can be written in this particular form that I'm about to show you here. Let's change the color if I can. It's a little bit hard to activate this thing. Here we go. All right. And so the thing, I used the word already, I didn't mean to because I wanted to introduce it first, but the thing we're dividing into is called the dividend. The thing we're dividing by is called the divisor. And you already have been introduced to these terms. We have a quotient and we have the remainder. So every division problem starts off like this. It starts off as dividend getting divided by a divisor. And the result will end up being a quotient, it's essentially the answer you get from your division, plus remainder, which in this case was 0, unfortunately. That was a bad choice on my part, picking a problem that had a remainder of 0. I didn't expect it for this one, because this part won't actually show up in our answer this time because it's 0. But if we had a non-zero remainder, we would have a number here that's still getting divided by the divisor, which is x minus 1/3 in this case. So the remainder is still getting divided by the divisor. All right, so every division problem has this structure to it. And so in this case, we have our quotient, which is the 9x squared plus 3x minus 15 plus the remainder, which for our example here is 0. So that fraction will just go away. We get 0 over x minus 1/3, which is going to be 0. So this is all you need to type in for your answer this time. If there was a non-zero remainder, we'd have this extra fraction here. All right, so that's how synthetic division works. We're going to be using it quite a bit in some problems coming up. Let's take a look at another concept now. So let me erase everything on the screen. Okay, sorry, I'm using some new software here, so I'm not 100% familiar with it. Before we move on, you can see on the screen here we have this other important formula for division. This really is just the same formula I just showed you, just it's been modified slightly. So let's take that formula we just had on the screen. We had dividend over divisor equals quotient plus remainder over divisor. And so all that's been done to achieve this formula right here is, sorry, I'm writing the wrong thing here. Let's see if I can erase that. Let's just see if I can do it. Okay, I can do it that way. Ah, it's bigger than I thought it would be. Okay. Let's try that again. Okay, over divisor. I can't do two things at once. Let me finish writing first. Okay, so all that's been done is the formula has been modified by eliminating the fractions. So what you can do to make this formula look a little bit nicer is get rid of the fractions by multiplying the common denominator to both sides, something that we have done multiple times in this course. So let's go ahead and do it for this. And even though there's no details here, the common denominator is the only denominator, which is whatever the divisor is. So we'll just multiply the divisor to both sides of this formula. We'll distribute it. Right, when we multiply to each of these, when we multiply to the fractions, we'll think of this as a fraction also, so divisor over 1. And when this gets multiplied to this fraction, the divisors are going to cancel out, and we'll just have the dividend left over. So we'll have dividend equals, the divisor gets multiplied to the quotient. We'll be stuck with both of those. So we'll have the divisor times the quotient. And then the divisor gets multiplied to this fraction, and again, the divisors will cancel out, and we'll just have the remainder remaining. All right, and so we get this formula here, and it turns out this formula plays a really important role in the concepts we're about to look at. So surprisingly, the formula for division will play some important roles here. So let's see, anything else I can think to say? So I think we're good on that. So let's take a look at the next concept. All right, so I'm going to erase this again. All right. Whoops. All right, bear with me on that. All right. Whoops. Here's what I want to do. Okay. So the next concept is what's called the remainder theorem. And we're going to take a look at, let's see, problem number 7 in conjunction with that. All right. So here's what the remainder theorem says. It's kind of an interesting idea, even though it's something you probably won't use. If R is the remainder, when a polynomial p of x is divided by x minus c, then R is equal to p of c. All right, so we have R is the remainder. If I can circle that accurately, okay. When a polynomial p of x is, so some generic polynomial, we're using function notation to represent, is divided by x minus c, so that means x minus c is the divisor. That's the thing we're dividing by. And p of x is the thing that's getting divided, so this would be my dividend. All right, so if you take all these components of the division problem here and plug them into that formula that we just had, so I'll have to write it on the screen again. We had dividend equals divisor times quotient plus remainder. So let's plug these elements into this formula here. The dividend, we're calling that p of x. That's the thing that's getting divided. So I'm trying to change the color here. All right. So the dividend P of x equals the divisor is x minus c, it's the thing we're dividing by. The quotient is the only thing that's not referenced in this theorem, so we'll just leave it as quotient, plus the remainder, which they want to call capital R just for simplicity, I suppose. So that's the setup, right? That's the if part of this theorem. The conclusion is that then R is equal to P of C. So let's confirm that conclusion by taking the setup that we just plugged into the formula and investigating this. So P of C means we want to take P of x, and in place of x, we're going to plug in the number c, whatever it happens to be. We don't know what it is, but it's some number here that already has been referenced in the divisor. So that's what we want to plug into the polynomial, which means everywhere there's an x, I want to plug in c. So I do the same thing on the right-hand side, and there's only one place where x is explicitly referenced, which is here in the divisor. In place of x, we're going to plug in c. We would do the same thing in the quotient, because I'm sure the quotient probably also has x variables, but since we're not being explicit about what those are, because it doesn't really matter in this situation, I'll just leave that as this. But we're doing the same thing here. Any x's that are located in the quotient, we're plugging c in for those x's as well. But what's going to happen is this part of it, the divisor, we get c minus c, which is 0. And so we'll have 0 times whatever the quotient is. So we'll get some answer from that. But that's also going to be 0, because 0 times anything is 0. And then we get 0 plus r, which ultimately just equals the remainder, which is the conclusion that they've drawn here. That P of c ultimately just equals the remainder from that division problem. So let's apply that to this problem here. Let f of x equal x to the third power minus 2x squared plus 8. Find the following function value using synthetic division. This is what they're referring to here, the remainder theorem. And then you can check it in the usual way by substitution, because that's how we'd normally answer a question like this. If you want me to find f of negative 3, I will substitute negative 3 into this function and find the answer. That's how I still do it. But the remainder theorem is providing us an alternate way of getting the answer. The remainder theorem is telling me that this will equal the remainder when f of x is divided by x minus whatever number you want to plug into your function. In this case, negative 3. So x minus negative 3, of course, becomes x plus 3. Right? So this polynomial will equal the remainder when the polynomial is divided by x plus 3, which we can do using synthetic division. All right, so I need to find some space here to work. I guess I'm going to have to erase this part right here. Let's just get rid of this. I don't need too much room, so maybe that'll be enough. All right, so let's go ahead and do some division. We'll set this up. All right, this is how we set up our synthetic division. C goes on the outside, and if you look at this, compare it to the formula, x minus c, c is going to equal negative 3, which is just the number that you're plugging into your polynomial to begin with. So the shortcut there is just whatever number you want to plug into the polynomial, that's what you'll use as your value for c. It's going to be negative 3. Across the top, we'll put the coefficients of our dividend, which is the polynomial we were given, starting with the highest power, 1, negative 2. Don't forget 0 because we're missing x to the first power, so we have to have 0 in there as a placeholder. All right, we'll start by dropping the first number below the box. It's going to be a 1. 1 times negative 3 is negative 3. You add these together, you get negative 5. Negative 5 times negative 3 is positive 15. You add these together, you get 15. 15 times negative 3 is negative 45. You add these together, you get negative 37, which is your remainder, which is all that I was interested in finding. So this is what f of negative 3 is going to equal. It's going to equal negative 37. So it's actually pretty fast. It actually works really well for finding the value of a polynomial. Rather than plugging negative 3 in and taking negative 3 to the third power, and then minus 2 times negative 3 squared, and being, careless with the negative signs there, that's a very real issue. We can find the answer pretty easily using synthetic division. Let's just check though to see if we get the same thing doing it that way. So if we were to do it in the normal way by substitution, we'd have negative 3 to the third power minus 2 times negative 3 squared plus 8. Negative 3 to the third power is negative 27. This will be positive 9, so negative 2 times 9 will be negative 18 plus 8. And we do indeed get negative 37 if you want to check that. Just make that into a part of the equal sign. So it works out. Get the same answer, but I think we get it quicker and easier using synthetic division. All right, so like I said, probably not going to change how you normally approach this kind of problem anyways, but it's an interesting idea, and we are going to exploit this idea with some other concepts that we're about to look at. So let's go ahead and move on to the next topic, which is the factor theorem. So let's go ahead and erase all of this and go to this here. So pardon me, I'm sorry, I'm talking to myself while I do this. Well, I want to talk about the factor theorem, but let's talk about this definition real quick. The zero of a polynomial. The zero of a polynomial p of x is any value of x such that p of x equals 0. So if a number, when we plug it in, would make the polynomial equal 0, then we give it the label of being a 0 of that polynomial. So it's a number that when you plug it in makes the polynomial equal 0. And so we call it a 0 of the polynomial. So for example, the last thing we just looked at, negative 3, is not a 0 of this polynomial because it makes the polynomial equal negative 37. It doesn't make it equal 0. But if negative 3, when we plug it in over here, made this equal 0, we would call negative 3 a 0 of this polynomial. So 0 here is being used not as a number, but as a label to describe what the number does to a polynomial when it gets plugged in. It makes it equal 0. All right. So here's the factor theorem. The number c is a 0 of the polynomial function y equals p of x if and only if x minus c is a factor of the polynomial p of x. All right. So if c is a 0 of the polynomial, the definition we just looked at tells me then if I were to plug c in to the polynomial, it would make the polynomial equal 0. That's what it means to be a 0. It's a number when it's plugged into the polynomial, makes the polynomial equal 0. If that's true, then according to the remainder theorem that we just looked at, this would be the remainder when p of x is divided by x minus c. That's the remainder theorem we just talked about, right? So putting those two together, going back to that division formula that we talked about earlier in the video, the dividend equals the divisor times the quotient plus the remainder. And if we take the elements of this problem and plug them into this formula once again, let's see, here's what it comes out to, right? So the dividend, the thing that's being divided, is again the p of x, right? P of x is being divided by x minus c. So the dividend's p of x. The divisor, the thing we're dividing by, is x minus c once again. The quotient is again not explicitly referenced, so we're just going to leave it as the word quotient. And the remainder in this case is going to be 0 if 0 is a polynomial of, sorry, not 0. If c is a I'm getting my words backwards now. If c is a 0 of the polynomial, that means the remainder must be equal to 0. And so we'll plug in 0 for the remainder. That's the remainder theorem. P of c equals the remainder when p of x is divided by x minus c. And if c is a 0, then p of c is equal to 0. So those two equivocate. The remainder must be 0. And if the remainder is 0, this just drops out, and we get that p of x is equal to x minus c times the quotient. And without the remainder component being there, what you have is two factors. So this is kind of a neat thing. right? These two things will now be factors. It's a neat thing because this gives us an avenue for factoring polynomials in a way that we couldn't factor them before. All we have to do is find situations where we divide and get a remainder of 0. Then we end up with a polynomial that is factored, right? Because we'll have x minus c as one factor, we'll have the quotient as another factor. And remember, factors are things that are being multiplied together. So these two things are multiplied now. There's no extra term being added or subtracted, so all we have are two factors here. Hence, our polynomial is now factored. So, and that confirms the conclusion of the factor theorem. If c is a 0, then x minus c ends up being a factor. And another aspect to that you're going to want to remember for when we do these problems, the quotient of your division will be your other factor, right? We actually end up getting two factors here. All right, so let's take a look at an example of how that is utilized. So let's take a look at number 8. Okay, sorry, it's I like the software, but switching between things is not entirely convenient. All right, so let's take a look at number 8. I guess I could have just hit next question. All right, so here's what they want to know. I'll just go and read the directions the way they're worded. Determine whether the given binomial is a factor of the polynomial following it. If it is a factor, then factor the polynomial completely. So the binomial that's at the start of the problem is x plus 2. And we want to know if that's a factor of x to the third power plus 4x squared minus 11x minus 30. And you might say, oh, if I want to know if x plus 2 is a factor, I'll just go ahead and factor the polynomial and see if x plus 2 is one of the factors there. And that would work if this is something that you were able to factor. But this kind of polynomial doesn't fit the form of the things that we've learned how to factor up until this point. So you actually are unable to factor this using previous techniques. You might be able to do it by trial and error, but it would be very difficult. It's going to be a lot more difficult using that technique. But you can't use, for example, what multiplies to 30 but adds to negative 11. That kind of thing's not going to work here. The only thing that we have learned previously that has some shot of working would be factor by grouping, but actually that doesn't work here either. So we're going to be using a whole new technique for finding factors for these kind of polynomials, and this is the technique we're going to use. If I want to know if x plus 2 is a factor of this polynomial, it would be a factor if p of negative 2, if that's equal to 0, right? If negative 2, because here c is equal to negative 2, right? If negative 2 is a 0 of the polynomial, then x plus 2 will be a factor. That's the factor theorem. That's what we're using up here. If x plus 2 is a factor, then c, which is negative 2 in this case, would have to be a 0 of the polynomial. So what I want to really find out is negative 2 a 0 of the polynomial? Because if negative 2 is a 0 of the polynomial, if it makes the polynomial equal 0, so this is the question right here, then x plus 2 would be a factor, and I could answer yes in this case. If negative 2 ends up not being a 0, then x plus 2 cannot be a factor of the polynomial. So how do I check to see if negative 2 is a 0 of the polynomial? I could take negative 2 and plug it in and see if it comes out equal to 0. But what we're going to do instead is use synthetic division. We're going to use the remainder theorem here and look at the remainder when this polynomial is divided by x plus 2, because not only is it quicker, but if it turns out that this is a factor of the polynomial, then we actually want to go ahead and factor it. And the other factor will be the quotient from this division. So if you're going to check this by just plugging it in, you're not going to be able to get the second factor that you need. So you really have to do it using division, using the remainder theorem. So we're going to take c, which is negative 2, put it on the outside here. Coefficients of the polynomial go across the top. So we have 1, 4, negative 11, negative 30. So we will start by dropping the first number below the box. So I'm trying to change color again. All right, so we'll drop the 1 below the box. 1 times negative 2 is negative 2. Add these together, you get positive 2. 2 times negative 2 is negative 4. You add these together, you get negative 15. Negative 15 times negative 2 is positive 30. You add these together, you get 0. The remainder is 0, which tells me that p of negative 2 equals 0, right? Equals that remainder, which tells me, sorry, that's supposed to be an arrow. Maybe I'll just do a arrow with one leg instead of two legs, which tells me that negative 2 is a 0 of the polynomial. That's the label we give it, right? Because that's what it does to the polynomial, makes it equal 0. And if negative 2 is a 0, according to the factor theorem, if that number is a 0, then x minus that number would be a factor. So if negative 2 is a 0, then x minus negative 2, which of course we would write as x plus 2, has to be a factor of the polynomial. So the answer is yes. We'll mark it over here, right? Yes. X plus 2 is a factor of the polynomial. And so, the short of it is, if there's a lot of ideas that make this work, and I want you to understand those ideas, and that's why I'm going through all this explanation. But if you really, the shortcut here is you want to divide x plus 2 into this polynomial, and if the remainder is 0, the answer is yes, x plus 2 is a factor. If the remainder is not 0, then the answer is no. So that's the simplest way that it could be put. Divide these two, see if the remainder is 0. Now, because the remainder is 0, we actually have some extra work to do. It says if it is a factor, then go ahead and factor this. So I want to go ahead and factor this polynomial. One of the factors will be x plus 2, the divisor, the thing we divided by. The other factor will be the quotient, right? So here's my quotient down here. So putting the variables back into it, it's going to be x squared plus 2x minus 15. So that's factoring it, but we can go one step further now because this result is now within the realm of things that I have learned how to factor previously. So here I can factor this by asking myself, what two numbers multiply to negative 15 and add to positive 2, right? And that's going to be positive 5 and negative 3. So I can go ahead and factor that even further, which is something that you need to go ahead and do. And then I'll just copy this factor down. Right? So now we have factored a polynomial that before knowing what we have just learned, you would not have been able to factor. None of the tools we've learned previously would help us factor this. So this is a new tool we're learning for factoring more complicated polynomials. All right, good. So let's take a look at another kind of problem that you'll come across on the homework. If I can get it to, there we go, erase. So let's look at number 10. All right. So here, this one's a little bit, it's in the same vein of what we just did, but it's just set up in a different way. They want to know if negative 5 is a 0 of this polynomial. And so we could check by plugging it in, and in this case, that actually would be okay because they're not asking us to factor. So we don't need to see what the quotient is. So if you just plugged it in to see if it equals 0, that would be one way to check, and it wouldn't harm you if you did it that way. But we're also supposed to be practicing what we're learning throughout this section. So for good practice, I would say let's go ahead and do it the way they want us to, which is using synthetic division. So if I want to know if negative 5 makes this polynomial equal 0, because that's what a 0 does, I can do that by using synthetic division and seeing if the remainder comes out equal to 0. If the remainder comes out equal to 0, this number is a 0 of the polynomial. If it does not equal 0, then it's not a 0 of the polynomial. So it really is as simple as that. And this is actually quicker. It's quicker to do this way than plugging it in using substitution. So let's drop the first number below the box. 3 times negative 5 is negative 15. You add these together, you get negative 1. Multiply, you get positive 5. Add, you get negative 3. Multiply, you get positive 15. Add, you get 0. The remainder is 0, so negative 5 is indeed a 0 of the polynomial. If I were to plug, what this tells me is that w of negative 5 equals 0, right? If the remainder is 0, the remainder theorem says that's what this polynomial equals when you plug that number into the polynomial. It makes it equal the remainder, which is 0 in this case. And the definition of what a 0 is, it's a number that makes the polynomial equal 0, right? So since negative 5 makes the polynomial equal 0, that's the label we give it. -5 is a 0 of the polynomial w of x, right? Because it makes the polynomial equal 0. And so that's why we're going to answer yes over here. All right, let's look at one more example like that. I'm sorry, I know I'm using the word 0 a lot in my sentences. I hope it's not too hard to follow. Sorry, I got to switch back to the pointer. So I wanted to look at this one as well. So same problem, same kind of problem. We're going to use synthetic division. C is -2 in this case. Whatever number you're checking on, that's what you want to use as your value for C. The coefficients go across the top, inside the box. We drop the first number below the box, multiply, add, multiply, add, multiply, add. This time, the remainder is -1, which again tells me something. It tells me if I were to take C, which is -2, and plug it into this polynomial, p of x, the answer will come out equal to -1, but that's not 0. So this tells me that -2 is not a 0 of p of x. All right, so I'd answer no up here. It's not a 0. It doesn't make the polynomial equal 0. It's not a 0 of the polynomial. Now, the penultimate problem in this section is being able to find all the zeros of a polynomial. So they're going to give you a polynomial and say, find all the zeros of this particular polynomial. Up until this point, they're giving me things to try. They're giving me numbers to check to see if they're zeros, or they're giving me polynomials to see if they're factors. So they're giving me some clues, and then it's basically a yes or no question. Either this thing worked or it didn't work. But what we ultimately want to be able to do is figure that out on our own. Give me the polynomial and let me figure out what numbers to guess and see if they work. And in order to do that, we need some more information. We need another concept. And so this concept is called the rational zero theorem. All right, so here it is right here. And it's kind of hard to see. I'm sorry if on my screen. Maybe I could, since this is the last slide, I'll just zoom it out and then close it when we're done. If you have this polynomial function, I know this looks scary, but this is just a generic polynomial. It starts with x to the n power, that's the first term, and it's going to have some coefficient, which we don't want to get specific about, so we just leave it as a. We're just going to label it as an a. And then you have your next term, which presumably would be 1 power less, right? So if you start with x to the third power, your next term is x to the second power, right? It's just 1 power less, so n minus 1, whatever the highest one is, but 1 less than that. And it also will have a coefficient, which we could use a different letter for, like b, but then we might run out because we don't know how big this polynomial is. So we're using a again, but to distinguish between the two a's, we are using subscripts. And what's nice about this is the subscript matches the power. So the coefficient of x to the n power is a sub n. The coefficient of x to the n minus 1 power is a sub n minus 1. And that would continue so on and so forth, n minus 2, n minus 3. And it's going to get lower and lower and lower, and so on and so forth, until you reach x squared, x to the first power, and then your constant. Right? And again, the subscripts match, 2's, 1's, 0. Right? This is some polynomial with integral coefficients, which means in order for this to work, the coefficients have to be whole numbers. That's what integral means. And let's suppose that we know a 0 already. P over Q is some rational 0 of f of x. The other limitation with this idea is that it only helps you find rational zeros, which are zeros that can be written as fractions, like 1/2, 1/3, or whole numbers, like 5, because that can be written as a fraction, 5 over 1. What we cannot find using this concept are imaginary zeros. This will have no way of finding those for you, or zeros that are like radicals, like square root of 2. So that's the limitation with this idea. Then P is a factor of the constant term a sub 0, and Q, the denominator here, is a factor of the leading coefficient a sub n. Right? So the numerator P would have to be a factor of the constant. The denominator Q would have to be a factor of the leading coefficient. So you might say, well, what good does this do me? Because this concept is presuming you have a 0 already and then telling you something about it. But this, the conclusion they're drawing here, will help us make better guesses for what could be zeros. So let me give you an example. All right, so I'm going to go ahead and close this. All right, well, now you can see my icons here. Now let me see if I can cover that up a little bit better. All right. So let's take a look at number 17. All right, so we have this polynomial, and what we're being asked to do is to find all the zeros of this polynomial, all the real and imaginary zeros, and they're giving us no leads, right? They're not saying try -2 to see if it's a 0. They're saying you're on your own with this. So we have f of x equals x to the third power plus 9x squared plus 11x minus 21. So I just mentioned off the top of my head, it's just a random number I just picked, -2. And so you might say, well, let's check. Let's check to see if -2 is a 0 of this polynomial. That's one of the numbers we checked previously. Let's just check that one again. Well, I can tell you right away that -2 has 0 chance of being a 0 of this polynomial. It's a waste of time to check this number. The reason being, if I write it as a fraction, -2/1, any 0 to this polynomial has to follow that rule that we just talked about, the rational zero theorem, where the numerator has to be a factor of the constant term, right? So the numerator is 2 in this case, right? If you think of -2 as a fraction, it's -2/1. The numerator is 2. This is our value. This is our value for p, right? And the denominator is our value for q. And the idea that we just looked at said that p has to be a factor of the constant term, which is -21. What are the factors of -21? You can ignore the negative sign. What are the factors of 21? 1, 3, 7, and 21, and that's it. So any 0 for this polynomial would have to have a numerator of one of these numbers here. The numerator has to either be a 1, a 3, a 7, or a 21. Any rational 0 would have to have one of these numbers as its numerator. This doesn't. This one doesn't have one of those numbers as its numerator, so this thing has no chance of being a 0 of the polynomial. So it'd be a waste of time to check that. Now, the denominator has to be a factor of the leading coefficient, right? So these are the values that p can equal. Here we have the leading coefficient, which is just a 1. And so the factors of 1 would just be 1. So there's no other factors there. And those are the values that q is allowed to equal. So q was okay here. We had a 1 here. That's all that q can equal. We were good on q, but p didn't match up, right? Our numerator didn't match any of the possible values that we can have for p. So this thing has no chance of being a 0. What numbers do have a chance of being a 0? Let's go ahead and put that together. Right? It would have to be a p divided by a q, where p is one of these factors of the constant, q is one of these factors of the leading coefficient. And so, for example, starting with this one here, 1 divided by 1 could be a 0 of this polynomial, because 1 is a factor of the constant, and 1 is also a factor of the leading coefficient. 3 divided by 1 could be a 0 of this polynomial. So again, that puts one of the factors of the constant as my numerator, another factor of the constant, and a factor of the leading coefficient as my denominator. 7 divided by 1 could be a 0. 21 divided by 1. Of course, dividing by 1 is a little bit silly to write that because 1 divided by 1 is still just 1. 3 divided by 1 is just 3, etc., etc. And so these would be all the possible zeros for this particular polynomial. If it's not on this list, it has no chance of being a 0. Now, these are just possibilities. I'm not saying that all of these are zeros. In fact, that can't be the case. Not all of these are going to work, but these are the only ones that have any shot at being a 0. The drawback is that we don't know whether it'll be positive or negative, so we have to consider both possibilities. It could be positive or negative 1. It could be positive or negative 3. All right, So these would be our best guesses right here. If you guess something that's not on this list, you're wasting your time. How do we check a guess? We pick a number from this list that we just made, and we use synthetic division to see if it's a zero of the polynomial. All I'm looking for is to see if the remainder comes out equal to zero. If I get a remainder of zero, then it's what I'm looking for. It's a zero of the polynomial. So that's, again, that's as simple as I can make it. We make this list of educated guesses. We check those guesses by doing synthetic division with them, with those numbers. And if the remainder comes out equal to zero, then that's what we're looking for. We can stop and factor. If the remainder doesn't come out equal to zero, we cross it off our list and we try something else. All right, so let's try a number from this list. And I'm going to pick a number because I kind of checked ahead of time to see what the answer is. So I wouldn't have to spend too much time because really you're kind of making guesses here. So you don't know which ones are going to work and which ones aren't going to work ahead of time. So, so we could, this list isn't too bad. There's only 8 things to check here, but you can have bigger lists and you might end up checking 5, 6, 7 different things and none of them work until the 8th one that you check. So I don't want to waste your time on the video checking a bunch of numbers that don't work. But I do want to show you just one time what happens when it doesn't work out. So let's try positive 3. Right? We'll put the coefficients of the polynomial across the top: 1, 9, 11, negative 21. We check by doing synthetic division, multiply, add, multiply. So 12 times 3 will be 36. Add these together, we get 47. And I'm not even sure what this is off the top of my head. Let's see, 120. I think it'll be 141. You might check me on that. And then, but clearly it's not going to equal 0. That, as soon as you realize that if you continue, there's just no way this will zero out, you can just stop, because I don't really care what the remainder is. All I care is whether it equals 0 or not. So if it's not 0, I don't really care how it turns out, right? So I think this will be 120, but that's not what we're looking for. The remainder is not 0. 3 is not going to work for me. Now, I should not completely dismiss 3 because I should check negative 3 as well, right? Positive 3 didn't work, but negative 3 is on this list. So let's go ahead and check negative 3. Now what you could do is you can actually just sort of erase what didn't work out here and start, kind of start over with a new number. And that way you kind of save space. But I kind of want to leave that on the screen to show, here's an example of what it looks like when it doesn't work out. Let's do an example of what it looks like when it does work out. So we'll have 1, 9, 11, negative 21 again, but this time we'll try negative 3. So we'll drop the 1 below the box. 1 times negative 3 is negative 3. You add these together, multiply, you get negative 18. Add these together, it comes out negative 7. Multiply, we get positive 21. And so we get a remainder of 0 this time, which is beautiful, right? That's what we're looking for. The analogy I like to give in class typically is that's like finding the golden ticket on Willy Wonka and the Chocolate Factory, right? So you found the golden ticket. Now you can do something. Now you can take action. Because when the remainder is 0, that means negative 3 is a 0 of my polynomial, which according to the factor theorem tells me that x minus negative 3 will be a factor, right? X minus negative 3, which we should write as x plus 3, is going to be a factor of this polynomial. Right? So if this is a 0, which we know because the remainder turned out 0, then this would have to be a factor. Right? That's the chain of logic that we're following here. So I can actually stop and factor this polynomial now that I have that information. So let's go ahead and do that. Let me change colors one more time here. And so I'll just do it right above the polynomial. So we're going to factor this now. X plus 3 will be one of my factors, x plus 3. The other factor will be the quotient from your division where you got the remainder of 0. So it's going to be x squared, 1x squared, plus 6x, because it's positive 6, minus 7. And so now we have managed to factor this thing that, again, before knowing this material, you wouldn't have been able to factor previously. And this can be factored even further using the old stuff that we had learned previously, right? So this is, again, a pretty simple one. You just have to find two numbers that multiply to negative 7, add to positive 6. That'll be positive 7 and negative 1. And the benefit of doing that is that we don't have to go back to this synthetic division to look for the other zeros, right? So negative 3 is one of the zeros, but there's probably going to be more. And we don't want to have to do it by synthetic division if we don't have to. This is really our last resort. We're only doing it this way because we have no other options. But once we get some other options, we're going to go with that. So as soon as I can stop doing synthetic division, then we do that, right? So as soon as we're able to stop it, we're happy about that, and we quit doing synthetic division, and we look for zeros in more convenient ways. So once I get it down to x squared, I can find the rest of my zeros by either factoring it manually, because that's something that we've learned how to do previously, or using the quadratic formula that can help me find the solutions to that. So this one actually factored nice, and then from these factors we'll get our zeros, right? We get x equals -3. That's one of our zeros. That's the one we already knew, but we get these two new ones that we just found. X equals -7 and x equals +1. All numbers which were on our list, but we don't have to find through synthetic division. We can find it this way instead. All right, so the three zeros for this polynomial would be -3, -7, and +1, and that's what you would type into the box. There were no imaginary zeros this time. All right. Sorry, I keep going off the window there. So again, this is something I'm hopefully will get better at the more of these I do. So let's erase that. Let's look at one more example. I'm trying to keep this video under 50 minutes, and we have about 4 minutes left. So I might go a little bit over. All right, erase. And I had another example that I wanted to do, but it's missing a component of something I wanted to talk about. So maybe I'll just switch to a different example. Let's see. Oh, okay. I'm taking a big gamble here at the end of the video, but let's go ahead and look at this one. So the other one I researched ahead of time and got some answers ahead of time. This one I have no idea what the zeros should be. So hopefully it doesn't take us too long to find them. Geez, okay, let's try that again. All right. So here is I just want to write it out to make sure everybody can see it okay. Minus 2x to the third power plus 46x squared minus 2x minus 5. So a couple things I'm hoping to address with this problem. One is that this is to the fourth power, so it's going to be a little bit more difficult whittling this one down, but also having something for the leading coefficient that isn't equal to 1, right? So we have 51 here, and that adds some extra complications to finding the zeros. So I wanted to make sure to do a problem where that was the case, so I'm not accused of just doing the easy ones, right? So again, to make our list of good guesses for what could be zeros to this polynomial, we want to identify the values that p can equal and the values that q can equal. And then we take every possible combination of a p divided by a q to generate our list of good guesses for what could be zeros here. P comes from the constant term. So what are the factors of 5? Well, this is kind of nice. It's pretty limited, just 1 and 5, right? Those are the only factors of 5. For q, so this is where we will find the values for p. This is where we find the values for q from the leading coefficient, which is 51, which is not a very nice number to see here. Now, 1 is always a factor of any number, and the number itself would also be a factor, 51. And I think the other two factors will be 3 and 17. So not that many, but not very pleasant numbers either. So hopefully that doesn't cause us too much grief. So to put our list of guesses together, we take every possible combination of a p divided by a q. So what I usually like to do is I like to start with the first value of p, which is 1, and then go through every value of q dividing by that value of q. So I'll have 1 divided by 1, which is 1. 1 divided by 3, which is going to be a fraction 1/3. 1 divided by 17, which is going to be an even worse fraction, 1/17. And then 1 divided by 51. Right. So that's every combination of p equals 1 with every value of q. And then now that I'm done with that one, I move on to p equals 5. Do the same thing. 5 divided by 1, which is 5. 5 divided by 3, which is 5/3. 5 divided by 17, which is 5/17, and then 5 divided by 51. And sometimes you'll get repeated values, like you might get 1/3 earlier on, and then you get 2/6 later, which reduces to 1/3. So sometimes you'll get values that get repeated, which you don't need to write twice on your list. This time we didn't luck out with that. Everything was a unique value. And then we also have to consider the positives and the negatives of that. And so these are all the numbers worth guessing for this particular polynomial. So now we need to sit down and try to figure out which one of these actually works. And like I said, I have no idea which one is correct. And so hopefully I won't make too many bad guesses before we find one that works. And so let's go ahead and make our guesses here. So I don't know, I'm having a good feeling about 1/3. I don't know, we'll see how that works out. So I'll put that at the top there. We have 51, -2, 46, -2, and then -5. All right, so let's see what happens here. So remember, multiplying by 1/3 is the same as dividing by 3. So 51 times 1/3 is 51 divided by 3, which is 17. You add these together, you get 15. That's promising. Now, if this wasn't divisible by 3, I'd quit right now, because if I end up getting a fraction at any point in my results here, it's not going to zero out. I need to get a 5 at the very end. If I'm starting to get like decimal numbers or fractions in this part of the problem, then it's not a good sign. But this works out. 15 times 1/3 is going to be 5, right? Because again, 15 divided by 3 is 5. You add these together, you get 51. Another good sign, because this will multiply nicely. 51 divided by 3 is going to be 17. We add these together, and so I am pretty lucky today. Maybe I should go play the lottery or go to the casino or something, because my first guess worked out good. So I ended up getting a remainder of 0, surprisingly. So once I get a remainder of 0, I take that information and I factor down my polynomial. So let me pick a different color here. I was going to pick blue again, but let's pick green. All right. And so one factor, because this is a 0, that means x minus that number has to be a factor. So x minus 1/3 would be one of my factors. The quotient that I got from this division would be another factor. So it's going to be 51 x to the 3rd power this time, because we go one less than what we started with, plus 15x squared plus 51x plus 15. Now this is still x to the 3rd power, and sometimes what you'll have to do is keep whittling this down until you get down to x squared, because once you get it down to x squared and it's quadratic, you know you can get the rest of the zeros from that. When it's still x to the 3rd power, we sometimes have to go back to doing more synthetic division. So what you would do is keep these numbers here that you just got as your result, and you could set up a new synthetic division box underneath those numbers and make another guess here and run through synthetic division and try to find another remainder of 0. So that would be worst case scenario. But in this case, we luck out because these numbers are following this nice little pattern of repeating like this. And so I can see that factor by grouping actually would work here. So instead of going back to synthetic division, I try to find any other way to do it. In this case, I can factor this, or I can find the rest of the zeros by using factor by grouping. So if you recall, the way factor by grouping works is you group the first two terms together in parentheses. Right? So I'll have 51x to the 3rd power plus 15x squared in one group. Start with a plus sign between your two groups, and then the second two terms will go into your second group there. I probably shouldn't use black because the text on the page is also black, and that's going to be hard to see. So I'll go back to red here. All right, so factor out the common factor in each group. It looks like 3x squared would be the common factor here if I had to guess. And that's going to give me 17x plus 5 left over. So yeah, that looked like a good choice. Here, the common factor is just going to be 3. And that's going to leave me with 17x plus 5. And this is how you know factor by grouping has been successful, when this leftover piece here matches this leftover piece here. If these don't match up, then factor by grouping was not successful. So we factor out the 17x plus 5 because it's a common factor in both of these groups. So we get 17x plus 5, and we're left over with 3x squared plus 3. Right, that's the leftover when we factor that out. And now this is factored. We'll copy this up to go with it. So we have x minus 1/3. And so now we have factored this polynomial down as far as we can, and we can get the rest of our zeros from these factors. So let me erase what we've just done here, if that's okay. I'm going to erase all this stuff here. What do I want to erase? Actually, I'll just erase the synthetic division stuff. So let's just erase all this since we're done with this part of the problem. And we'll just continue underneath here. So this factors as x minus 1/3 times 17x plus 5 times 3x squared plus 3. All right. Now to find the zeros, we set each factor equal to 0. Here we're going to get the same 0 that we found from synthetic division, so nothing new there. This one, we're going to set this equal to 0. We get 17x plus 5 equals 0. And then you'll solve that for x, and I'll spare you the details because I'm already a little bit over time. But I assume you should have no problem getting that. You'll get negative 5 over 17, which if you go back to the list that we had, this would have been one of the numbers on the list, but it would have took us a while to probably get around to checking that one. This one we set equal to 0. And you subtract 3 from both sides. And so you get 3x squared is equal to negative 3. Divide by 3 on both sides, you get x squared is equal to negative 1. You take the square root of both sides, and you get x equals square root of negative 1 is I. It's the imaginary number. So this we would have never found from our list because it's an imaginary number. And the process we're using doesn't find imaginary zeros. It doesn't find radical zeros. Not only do we get the imaginary number because square root of negative 1 is I, but we also, because we took the square root of both sides, have to use a plus or minus. So we actually get 2 zeros from this. We get positive I and we get negative I. All right, so we actually have 4 zeros here altogether. 1/3, negative 5 over 17, positive I, and negative I. We got 2 imaginary zeros in this case. So that is section 3.2. If you're one of my students watching this video, please let me know if you have any questions when we meet together in class again, or feel free to email me if you'd like to do that. And hopefully you'll get the hang of this. It just takes a little bit of practice. I know it's a lot of complicated ideas and the process is fairly long, but with practice, I think students get pretty good with this. So you just need to practice it and I think you'll be fine. All right. Sorry. See you later.